Hi everyone, thanks for tuning in. This is Nate, a Murph synthetic voice talking to you from Gradient N. In this video we set up and train a fully connected image classification neural net and a couple of convolutional nets using the vegetable image dataset downloaded from Kaggle. The link is in the description box below. The vegetable image dataset includes 15,000 training, 3,000 validation, and 3,000 test images of 15 types of vegetables. There are green beans, bitter gourds, bottle gourds, brinjal or eggplant, broccoli, cabbage. There are a lot of green vegetables. Capsicum or peppers, carrots, cauliflower, cucumber, papaya, potato, pumpkins, mostly green, radishes, white, and tomatoes, green to red. We'll go ahead and set our selection type to folder and select the train data folder. Once the images load, we'll change the image sizes from 200 by 200 to 100 by 100 pixels to help speed training. To set up our fully connected net, we'll insert an image layer in the drawing area. Then we'll select Net from the toolbox and click out on the drawing board. We can turn our Input and PreProcess nodes off. Set our hidden layers to 3 and hidden layer width to 12. And set the number of output nodes to 15. We'll leave our activation functions as sigmoid for now. We can then place the net where we like on the drawing area. Next, we'll auto-route the connections from the image layer to the net. After fitting the net to the drawing area, we'll go ahead and change our hidden nodes to Relu. Then we can connect the net outputs to their vegetables. We'll connect to bean, bitter, bottle, brinjal, broccoli, cabbage, capsicum, carrots, cauliflower, cucumber, papaya, potato, pumpkins, radish, and tomato. Finally, we'll select validation data files. And then select the validation folder for our validation set. We'll save our net as VegetablesFully. Then we'll reduce the net window and get the net ready to train. Next, we'll set up a convolutional net in our center instance of NNetDesigner. We'll open the VegetablesFully design. We'll move the image input layer to the left and the fully connected net to the right to make room for a convolutional layer. Then we'll delete the input connections to the net and place a convolutional net in their place. We'll move the fully connected net to the right a little more to make things look nice. And now we auto-route the net together. Finally, since we're adding the convolutional layer, we'll remove one of the fully connected layers. And route the net back together. If we look at the properties of the convolutional layer, we see that it is a hidden layer of image data and that all the standard net properties are available. We can set input convolutional sizes and strides, and output convolutional sizes. We'll go ahead and leave the default properties for the convolution. And save the net, naming it VegetablesConv1. We'll then reduce the net window size and set the net up to train. For our last net, we'll bring out the Properties window and open the VegetablesConv1 net. After selecting our convolutional net, we'll change our input size from 4 by 4 to 8 by 8 pixels, with strides of 8 by 8. Then we'll change our output size from 2 by 2 to 4 by 4 pixels. We're increasing the convolution sizes but keeping the reduction from input to output the same. After closing the Properties window, we'll save the net as VegetablesConv2. Then we'll reduce the size of the window and set it up for training. We'll start training for all 3 nets. Let's fast forward through training initialization. And fast forward through training startup. We stop training for each net when validation performance appears to have stabilized. The red traces on the training graphs indicate validation performance. We're targeting best validation performance, and so, even though it looks like training performance, the blue trace on the graphs is still improving. We want to be careful not to overtrain. We can see that the fully connected net on the left has finished training in under 4 hours, while the middle 4 by 4 to 2 by 2 convolutional net has taken about 17.5 hours to train. And the 8 by 8 to 4 by 4 convolutional net on the right has taken almost 27 hours to train. We'll open the data output windows for each net. And save their data so we can view their classification matrices in Excel. When we open the data file for the fully connected net, we see that classification performance is pretty poor, with a training classification accuracy of 17.8% and a validation accuracy of 16.8%. We can also see that, while we would like good matching along the diagonal of the matrices, the match between inputs and outputs isn't very good. With vegetables with distinct colors, the net has done an okay job of identification, but otherwise simply isn't able to train. Without much difference in colors for many of the vegetable images, the fully connected net doesn't have much to work with. The situation is much better with the first convolutional net, with the 4x4 to 2x2 convolution. Convolutions can use color but are also better at finding patterns in shapes. Training accuracy for the 4 to 2 convolutional net is 98.3%, and the net has a validation accuracy of 75%. We can also see that the train to data match along the diagonal of the matrices is pretty good. While the training accuracy for the 8x8 to 4x4 convolutional net is slightly worse than the 4 to 2 convolutional net, it is still good at 98.1%. The validation accuracy, which is what we really care about, is better for the 8 to 4 convolutional net, though, at 80.2%. And the data match along the diagonals is still pretty good. With the designs we've shown and with the vegetable images dataset, convolutions have performed significantly better than a simple fully connected net. In this video we've shown how to set up convolutional nets with NNetDesigner for image processing. We've also shown that we can improve validation performance by adjusting convolution sizes. Of course, there are many design options available, such as working further with convolution sizes or changing activation functions, for potential further improvements in net performance. Thanks for watching. We'll see you next time.